Welcome back to TalkTensors, where we kind of like really get into the latest machine learning research, And today, we're diving deep into this paper that's all about making those big, huge language models run smoothly and efficiently. The paper is called Queuing, Predictions in LLMs, Challenges and Open Problems.
Yeah, so this is a really timely topic, right?
Mm-hmm.
LLMs are everywhere now, and they're only getting bigger and more complex, so figuring out how to serve them efficiently is absolutely crucial.
Right, like we all love those amazing things LLMs can do, but behind the scenes, there's a ton of computation going on, right?
Yeah.
And that's where this research comes in. It's looking at how we can use prediction to kind of like optimize the whole scheduling of these big AI workloads.
Exactly. And the cool thing is this paper actually brings together two fields that haven't always talked to each other that much.
Yeah.
You have queuing theory, which is all about analyzing waiting lines and optimizing things like, call centers or factories. And then you have this very recent explosion of LLMs with them unique computational needs.
Okay, so like queuing theory meets LLMs.
Yeah.
What's the history here? How did we even get to this point where these two fields are coming together?
Well, queuing theory's been around for ages, right? People have been trying to understand how to make things flow smoothly in all sorts of systems. You think about lines at the bank or traffic jams or even how your computer operating system handles tasks. They've all got these queuing problems at their heart.
Right. It's all about making sure things don't get stuck waiting too long, right? Minimizing those waiting times and getting things done as quickly as possible.
Exactly. And early on, the solutions were pretty simple, first come, first served, FIFO, right? Whoever gets in line first, they get served first. But then researchers realized, hey, if we actually knew how long each job would take, we could do much better.
So if you knew some tasks were super quick and others were going to take forever, you could prioritize the quick ones, right?
Exactly. And that led to things like SRPT, shortest remaining processing time. It's a much smarter way to organize the queue, but it relies on knowing those processing times, which in the real world often isn't realistic.
Okay, so that's where the prediction piece comes in, right? We can't always know those processing times exactly, but maybe we can make some educated guesses.
That's the heart of it. Instead of assuming we have perfect information, we say, okay, what if we can predict those job sizes, even if it's not perfect? How can we use those predictions to still make better scheduling decisions? This whole algorithms with predictions paradigm emerged, and it really changed how we think about designing these systems.
So it's not just about the algorithm itself, but about how it can be supercharged with machine learning models that can predict those important job characteristics, right?
Exactly. And a big part of this research is analyzing how well those learning augmented algorithms actually work. How consistent are they? Meaning, do they perform well when the predictions are good? And how robust are they? Meaning, do they still work okay when the predictions are way off?
Makes sense. You don't want your whole system to fall apart if the predictions aren't perfect.
Absolutely. And this is where LLMs come in. Because they're so different from traditional workloads, they need a whole new way of thinking about scheduling. They're not just processing a set amount of data, right? You've got this iterative generation of text, and the memory footprint, especially with this thing called the KV cache, it keeps growing as the model generates its response.
Okay, yeah, the KV cache, that's something we've talked about before on TalkTensors. It's basically like the LLM's short-term memory, right? Where it keeps track of what it's already generated so it can generate the next part of the response efficiently.
Precisely. And because it's constantly growing, it throws a real wrench in the works when it comes to traditional scheduling techniques, like preemption.
Preemption, meaning interrupting a task to give priority to something else, right? Like if you have a high priority request coming in, you might pause something that's already running.
Exactly. In a regular system, preempting a task might just be about saving a little bit of state information. But with LLMs, you might be dealing with gigabytes of KV cache data. You can't just throw it away because then you'd have to recompute it later, which is super inefficient. But keeping it all in memory eats up space that other requests might need. And moving it around takes time, which slows things down.
So it's like a balancing act. You want to be responsive to new requests, but you also don't want to be constantly preempting things and incurring those huge KV cache overheads.
Exactly. And this is one of the key challenges this paper highlights. It's not just about scheduling based on processing time anymore. You have to factor in this whole memory management aspect as well. And then on top of that, you have the two-stage process of LLM inference, prefill, and decode.
Right. Can you remind us again, what's the difference between those two stages?
Sure. Think of it like baking a cake, right? Prefill is like gathering all the ingredients and getting everything ready. It's computationally intense, but you can often do it in parallel. In the LLM world, this is where you process the input prompt and set up the initial state of the KV cache.
And then decode is like the actual baking process, right? Where you carefully combine those ingredients and create the final product.
Exactly. And just like baking, decode in LLMs is more sequential and memory bandwidth limited. You're generating each word one at a time, and each new word depends on the ones that came before it.
So you've got these two very different phases, each with its own resource requirements. And the paper's basically saying you need a scheduling system that's smart enough to handle both of them effectively.
Exactly. And it goes even further, highlighting that we need new theoretical models and algorithms that are specifically designed for the unique demands of LLM inference. The classic queuing models just don't quite cut it anymore.
So let's dive into those challenges and open problems, right? The paper starts by looking at how we can use predictions in more general queuing systems, even outside of the LLM world. What are some of the key ideas there?
Yeah, so the paper reminds us of the basics of queuing theory, right? Things like the MG1 queue, which is just a fancy way of saying you have one server handling a bunch of incoming jobs. In a simple scenario where you don't know anything about how long those jobs will take, FIFO is the default. But if you knew the exact processing time of each job, you'd use SRPT, shortest remaining processing time, because that minimizes the average time jobs spend waiting.
Okay. But as we've already discussed, in reality, we often don't know those processing times. That's where predictions come in.
Right. So the big question becomes, if we have predictions, how good do they need to be to actually help? And what are the best ways to incorporate those predictions into our scheduling algorithms?
The paper talks about things like SPRPT, SPJF, and PSGF. I know those are all acronyms, but can you break them down for us?
Sure. So SPRPT is just like SRPT, but instead of using the actual processing time, it uses the predicted processing time. SPJF, shortest predicted job first, does the same thing, but for jobs that haven't started yet. And PSPJF adds preemption to the mix, so you can interrupt a longer job if a shorter one arrives.
Okay, so they're basically the prediction-based versions of those classic scheduling algorithms.
Exactly. And the paper discusses a framework called SOAP that can be used to analyze how well these kinds of algorithms perform, as long as the scheduling decisions are based only on the job's inherent characteristics and the service time so far.
Now, there's this whole thing about one-bit predictions that caught my eye. It sounds almost too simple to be effective. What's the idea there?
It's a really cool concept. Imagine you don't have a precise estimate of how long a job will take. You just have a binary prediction, short or long. That's it. What's amazing is that even this limited information can significantly improve performance compared to having no prediction at all.
Wow, just knowing short or long can make that much of a difference.
Yeah. It turns out, especially when you have these long jobs that can really clog up the system, just being able to identify them, even roughly, is super valuable. The paper even gets into some pretty heavy math to show how much of an impact those one-bit predictions can have, depending on the kind of workload you have.
Okay, so it's not just about the accuracy of the prediction itself, but also about what kind of information is most helpful for the scheduler, right? Mm-hmm. In some cases, just knowing short versus long can be a huge win.
Exactly. And the paper also emphasizes that the cost of getting those predictions is a factor too. Running complex machine learning models to get those predictions takes time and resources.
It's like if the prediction itself takes longer than the job you're trying to schedule, that's not very helpful.
Exactly. So the paper discusses algorithms like skip predict and delay predict, which are all about, being smart about when to invest in getting those predictions. Like, maybe you only bother with a more accurate prediction if the initial, cheaper prediction suggests the job is likely to be long. Or you start processing jobs FIFO and only switch to a more complex scheduling strategy if a job runs longer than expected.
So it's all about being cost aware, right? Weighing the benefits of better scheduling against the overhead of obtaining the information you need to do that scheduling.
Right. Now, all of that is focusing on single server systems. But of course, in the real world, we often have multiple servers working together.
And I imagine things get a lot more complex when you have to coordinate across multiple servers, right?
Absolutely. Most of the theoretical work in queuing theory with predictions has focused on the single server case. The multi-server setting is a lot trickier, and there's still a lot of active research going on there. The paper does mention some recent progress using this thing called fluid limit analysis, but it's definitely an area where we need more work.
Okay, so that gives us a good overview of how predictions can be used in queuing systems in general. But now let's turn our attention specifically to LLMs. What makes them so unique and challenging from a scheduling perspective?
Well, as we've touched on already, one of the biggest things is that KV cache, that growing memory footprint. Unlike traditional tasks where you have a fixed amount of data to process, LLMs are constantly updating this cache as they generate their output. And that has major implications for how we approach things like preemption.
Because interrupting an LLM mid-generation might mean having to deal with gigabytes of KV cache data, right?
Exactly. And that creates a whole new set of trade-offs. Do you keep that cache in fast GPU memory, taking up space that other requests could use? Do you try to move it to slower CPU memory, incurring a time penalty? There's no easy answer, and it really depends on the specific workload and the hardware you're working with.
And then on top of the KV cache, you've got the two-stage nature of LLM inference, prefill, and decode. Can you remind us again why that matters for scheduling?
Yeah, so prefill, that's where the LLM processes the input prompt and kind of gets itself ready to generate the output. This stage is often computationally intensive, but it can often be parallelized across multiple GPUs. Decode, on the other hand, is where the LLM actually produces the output, one token at a time. This stage is more memory bandwidth bound and can't be parallelized as easily.
So it's like you need a scheduling system that can juggle these two very different types of tasks, right? Making sure the prefill stage has enough computational power and the decode stage has enough memory bandwidth.
Exactly. And the paper discusses some recent systems that are specifically designed to do this, things like Orca and VLLM, which use techniques like dynamic batching and page detention to try to optimize both phases.
So given all these unique challenges, what are some of the specific approaches and open problems that the paper highlights when it comes to scheduling in LLM sorting systems?
Well, one of the biggest challenges is just dealing with the unknown output length of LLM requests. Unlike a lot of traditional computing tasks where you have a pretty good idea up front how much work needs to be done, with LLMs, the length of the generated response can vary wildly depending on the input and the model's internal state.
Right, because the LLM might decide to generate a short, concise response or a long, rambling one.
Yeah.
And that makes it really hard to predict how much time and resources a particular request will need.
Exactly. So the paper discusses a bunch of different techniques that people are exploring to try to predict output length. Some use separate, smaller LLMs to make those predictions. Others try to fine-tune existing models like BERT for this specific task. And there are even some that use learning to rank approaches.
So it's like we're using machine learning to predict how much work another machine learning model will do.
Exactly. And it's a tricky problem because those predictions need to be accurate enough to be helpful, but they also can't be too expensive to compute.
Right, it's that cost awareness thing again.
Right. Now, one interesting system that the paper mentions is called Trail. It uses this technique called probing to predict output length.
What is probing exactly?
It's kind of like a test run. Instead of using a separate prediction model, Trail actually runs the LLM itself for a very short period to get an early indication of how much output it's likely to generate. It's like you're peeking into the LLM's mind to see what it's thinking.
That's clever. So it's using the LLM's own behavior to predict how much work it will do.
Exactly. And then based on that prediction and how far along the request is in its generation, Trail makes decisions about whether to preempt it or let it continue running.
So it's balancing responsiveness to new requests with the cost of interrupting those longer running requests.
Exactly. And beyond predicting output length, the paper also talks about the need for more adaptive scheduling systems that can take into account other factors like cost constraints, different types of hardware, and even the possibility of prompt sharing, where multiple requests might be able to share parts of their KV cache.
Prompt sharing. That's an interesting idea. It's like carpooling for LLMs.
In a way, yeah. If multiple requests are asking similar questions or using similar prompts, they might be able to reuse some of the computations that have already been done, saving time and resources. Systems like SGLang with Redix attention are designed to take advantage of these kinds of opportunities.
And then on top of all that, you also have to think about the different types of requests that might be coming in, right? Some might be interactive, requiring very low latency, while others might be more batch-oriented and tolerant to delays.
Absolutely. And this is where things like service level agreements or SLAs come in. You might have different guarantees for different types of requests, and your scheduling system needs to be able to enforce those guarantees. Systems like SageServe are specifically designed to manage these kinds of diverse workloads.
It's like you need a whole air traffic control system for LLMs, making sure everything runs smoothly and everyone gets where they need to go on time.
Right. And even the hardware itself becomes a factor in scheduling. The paper discusses different strategies for allocating GPUs, like having a pool of shared GPUs versus dedicating specific GPUs to prefill and decode.
And I imagine moving that KV cache around between GPUs can also be a bottleneck, right?
Exactly. So the ideal strategy really depends on the specific hardware architecture and the types of requests you're handling.
It's fascinating how all these different pieces fit together. And it's not just about individual LLMs anymore, right? The paper also talks about these more complex AI systems that combine LLMs with other tools.
Yeah, so now you have LLMs that might be making calls to external APIs to retrieve information or perform actions in the real world. And that introduces a whole new layer of complexity for scheduling. Do you pause the LLM while it waits for the API call to return? Do you try to swap out its KV cache to free up memory? These are all open questions that researchers are still grappling with.
And what about scenarios where you have multiple LLMs working together? Like maybe you have a smaller, faster LLM for initial responses and a larger, more accurate one for more complex tasks.
Yeah, that's becoming more common, and it introduces this whole problem of intelligent request routing. Which LLM is best suited for a particular request? Do you send it to the fast one or the accurate one? Systems like RouteLM are trying to address this by taking into account things like model size, expected runtime, and the desired level of accuracy.
And then you have even more complex systems where multiple LLMs might be working together in sequence, forming a chain or a graph of tasks that need to be executed.
Right. These are often called agent-based or DAG-based models, and they pose even more challenges for scheduling because you have to manage those dependencies between the different LLMs.
So it's not just about scheduling individual tasks anymore. It's about scheduling entire workflows of tasks.
Exactly. And the paper also touches on this really interesting area of LLM reasoning systems, where the LLM is performing more complex cognitive tasks.
Can you give an example of that?
Yeah, so instead of just generating text based on a prompt, the LLM might be engaging in something like multi-step reasoning, where it has to explore different possibilities, gather evidence, and come to a conclusion. This kind of reasoning often involves a lot more back and forth between the LLM and its memory, making the scheduling problem even more complex.
So it's not just about the length of the output anymore. It's also about the complexity of the thought process that the LLM is going through.
Exactly. And that means we need even more adaptive and dynamic scheduling systems that can respond to the LLM's internal state and adjust resource allocation as needed.
Okay, so pulling it all together, it seems like efficient scheduling for LLMs is a really complex and multifaceted problem. It draws on ideas from traditional queuing theory, but also presents a whole new set of challenges that are unique to these large language models.
Absolutely. This paper really highlights the need for new theoretical frameworks and practical algorithms that can address the unique demands of LLM inference and the increasingly complex AI systems that are being built around them.
And for our listeners, the takeaway here is that as these AI models become more powerful and more ubiquitous, being able to run them efficiently is going to be absolutely crucial. It's not just about throwing more hardware at the problem, it's about understanding the nuances of how these models work and how to best allocate resources to meet their needs.
Right. And it's a rapidly evolving field. What works today might not work tomorrow, so it's important to stay on top of the latest research and be willing to adapt as these models continue to change.
Absolutely. So speaking of staying on top of things, let's move on to our Novel Notions segment, where we like to brainstorm some potential future research directions inspired by the paper we've discussed.
Sounds fun. What do you have in mind?
Okay, so we talked a lot about predicting output token length as a key factor for scheduling. But what if we could predict more about the nature of the request itself?
That's an intriguing idea. So not just how long the response will be, but what kind of task the LLM is actually performing.
Exactly. What if, right when a request comes in, we could classify it as, say, a factual query, creative writing, code generation, or something else?
Interesting. And then we could use that information to make better scheduling decisions, right? Like a factual query might be handled by a smaller, faster LLM, while a creative writing task might need a larger, more powerful one.
Exactly. I'm thinking we could even take it a step further and have a multi-level prediction system. Like first you classify the task, and then you predict the output length based on the task. And then for certain types of tasks, you might even predict other things, like whether the LLM will need to make external API calls.
Okay, I like where you're going with this. So it's like a prediction cascade, right? You start with a high-level classification and then get more and more specific as needed. And each level of prediction can inform the scheduling decisions.
Exactly. It's like giving the scheduler a much richer understanding of what each request actually entails, rather than just treating them all as generic jobs.
This could be really impactful, especially for systems that handle a wide variety of tasks. You could prioritize those short, factual queries for low latency while giving those more complex, creative writing or reasoning tasks the resources they need to really shine.
Okay, here's another one, building on the whole KV cache discussion. What if we used real-time telemetry from the KV cache to make more dynamic preemption decisions?
Oh, that's interesting. Explain that one a bit more.
So instead of just relying on initial predictions, we could actually monitor how the KV cache is behaving for each active request. Like how quickly is it growing? Are there any patterns in the way it's being accessed?
So it's like using the LLM's own memory usage as a kind of real-time feedback signal.
Exactly.
Yeah.
And based on that feedback, we could adjust the preemption thresholds dynamically. Like if a request that was predicted to be short suddenly starts rapidly expanding its KV cache, maybe that means it's more complex than we thought and we should avoid preempting it.
Right. Or on the flip side, if a request that was predicted to be long is actually showing very slow KV cache growth, maybe it's a good candidate for preemption to free up resources for other requests.
Exactly. It's about making the scheduling system more responsive to the actual behavior of the LLM, rather than just relying on those static predictions.
I really like that idea. It could be a great way to mitigate the negative impact of those inevitable prediction errors and make the whole system more robust.
And of course, these are just speculative ideas. There's a lot more research that needs to be done to explore these possibilities and see how well they work in practice.
Absolutely. But that's what makes this feel so exciting, right? There's so much we still don't know, and there are so many opportunities to make a real impact.
Absolutely. Well, that brings us to the end of our deep dive into queuing, predictions, and LLMs. As always, we've just scratched the surface here, but hopefully we've given you a taste of the fascinating research that's going on in this area. If you're interested in learning more, you can find a link to the paper in the show notes below.
And if you have any thoughts or ideas of your own, we'd love to hear them. You can reach out to us on Twitter or join the discussion on our Discord server.
Absolutely. Thanks for joining us on TalkTensors, and we'll see you next time for another deep dive into the world of machine learning research.